Hello everyone, today we're going to be working on the properties of real numbers, and we should have already gone over classifying real numbers. So you should know what a real number is, and it's any number that we're going to be working with in this class. So we have some properties of real numbers, and the idea that we're going to try and pass along is that each of these properties have some sort of algebraic technique with them. So what we're going to do today is we're going to go through and I'm going to give you some notes on the properties of real numbers. So first off, you should know what to do by now. There's going to be a blank copy of the notes in the same folder that you found this video. Go ahead and download that and get ready, print it out if you can, but take notes on this, and at the end of the video I'm going to ask you to take a picture of your completed notes and upload them to this folder so I can give you credit for watching this video. After that, I need you to keep these notes in your binder, and whenever we return back to school, if we return, I'm going to collect your binders and grade them accordingly to make sure that you kept up with everything that I asked you to keep up with. So, to begin, we're going to talk about the cumulative property and commutative property of addition or multiplication. So what that means is that the main idea of it is the order of the values doesn't matter. So we could have, for addition, b plus a is equal to a plus b. And this makes sense because if we have 2 plus 3 is equal to 3 plus 2, we understand that that's the same thing. But that's called the commutative property of multiplication, or commutative property of addition. So for multiplication, it's similar, but of course instead of addition we're going to have multiplication. And for this one I'm going to use x and y. So if we have x times y, we know that that's equal to y times x. And we understand that from a given point. So again, if we have this an example like 5 times 4, we know that's the same thing as 4 times 5. But that's just an understanding that we've had since early middle school or late elementary school. We understood that if you multiply two numbers together, it doesn't really matter the order, and if you add two numbers together, it doesn't really matter of the order. But the name of this property is the commutative. And again, the order of the values does not matter. Moving on to the associative property of multiplication or adding. So with this, we can say that grouping doesn't matter. So the grouping of the values does not matter. So for example, for addition, we could have the grouping of a plus b, and then we add c to it. We know that that's the same thing as having a plus the group of b plus c, because they just all add together. So a plus b plus c. Doesn't matter that they're grouped together differently. And an example of this that we could give would be 5 plus 1, and that's grouped together. And then we're going to add 3. And then we have 5 plus the grouping of 1 plus 3. We know that on both sides of the equal sign it's equal to 9, because 5 plus 1 is 6, 6 plus 3 is 9. So, for multiplication, we have, again, I'm going to use letters, and this time I'm going to keep it A, B, and C. So I could have the grouping of A times B multiplied by C, and I know that's equal to A multiplied by the grouping of B times C. An example of this could be 2 times 4 grouped together multiplied by 7, or 2 times 4 times 7 in a group. And we know that both sides of the equal sign, well, 2 times 4 is 8, and 8 times 7 is 56. And we know that on both sides of the equal sign, those two values are going to be the same. So it's going to be 56 is equal to 56. So we know that associative property holds. So what I need you to be able to do is look at something and tell me if it's associative, or tell me if it's using the commutative property. Next, we have something called the identity property. The identity property of multiplication or addition, the main idea of it is that it just stays the same. So for addition, what could we add to something to make that something stay the same? So in other words, A plus what gives us A? And your answer should be 0. So we have that if we add, we're able to add something to get the same thing. So if we have A plus something equals A, we know that we're only adding 0. So that's for addition. Now multiplication, we can have A times something is equal to A. So what can we multiply A by to get A? Well, it would just be 1. Because anything multiplied by 1 is whatever was multiplied. So we have that if you multiply by A, or multiply by 1, nothing happens. It just stays the same. So that's the identity property of addition and multiplication. Now we have the inverse of the inverse property of addition and multiplication. Basically what I'm saying is they are opposites. So we're using the opposite operation to cancel a value. So if we think about it, if we have A plus something and we want to cancel out, or in other words, we want that to equal 0, what can we add? Well, we can just add negative A, or the opposite of the value. Another one is for multiplication. If we have A multiplied by something and we want that to equal 1, because that's how we cancel things out with multiplication, what would we have to multiply by? Well, by this we're saying the opposite. So the opposite of A would be 1 over A. So this is called the inverse property of addition and multiplication. So again, the main idea of it is we're using the opposite to cancel a value. So again, we're using the opposite to cancel a value. Next is probably the easiest one you'll see. We have the property of 0, meaning multiplying by 0 always equals 0. So I'll give you a few examples. If we have 17 multiplied by 0, well, that's definitely going to give us 0. So I can say if we have any number multiplied by 0, it's also going to be 0. And finally, if I have any fraction, even a negative fraction, multiplied by 0, well, anything multiplied by nothing is nothing. So we have that anything multiplied by 0 is 0. Next, we have the distributive property. The distributive property means that we're multiplying. So we're going to multiply a value to an expression inside parentheses. So you've done this before without even realizing it. You used the distributive property earlier in one of our assignments. So for example, if you have A multiplied by B plus C, what we do is we distribute the A. So we say, well, A times B plus A times C. So that A just is multiplied by everything inside of the parentheses. Another example is we could have 2 multiplied by x plus 7. So we use the distributive property, where we say 2 times x and then 2 times 7. So 2 times x is 2x, and 2 times 7 is 14. So we're going to add 14. And finally, one last example. If we have negative 5 being distributed across y minus z, we have that as negative 5 multiplied by y and negative 5 multiplied by negative z. So negative 5 multiplied by y is going to be negative 5y. Negative 5 multiplied by negative z, well, two negatives multiplied together gives us a positive, and then 5 multiplied by z gives us 5z. So these are some properties of real numbers. We're going to move on to the second page, and we're going to talk about some more properties of real numbers. Okay, so the first property that we're going to talk about on this page is called the reflexive property. Basically, it means that a value always equals itself. So in other words, A is always equal to A. Some examples. We have 16 is equal to 16. That's, pretty easy to understand. We have 5x is equal to 5x. And again, this is using the reflexive property. So think of it like a mirror. The equal sign's a mirror. And we have one reflection of 5x on this side. Then we have the equal sign. And then we have a reflection on this side. So we have 5x is equal to 5x. And finally, we could even have 4y squared is equal to 4y squared. And we know that that's true using the reflexive property. Next, we have the symmetric property. Now, the symmetric property is something called an if-then statement. So we have that if A is equal to B, then we have that B is equal to A. And that makes sense, because if A is equal to B, then of course B is going to be equal to A. We can flip it across the equal sign, so it doesn't really matter. And we could write that out like if x is equal to 3, then we can say 3 is equal to x. Or we can say if 5x is equal to 30, then we have that 30 is equal to 5x. We're just showing that the equal sign, we can flip the numbers around or flip anything around the equal sign as long as it doesn't change sides, like as long as both things stay on the same side of one another, it doesn't matter. So we can say x is equal to 2 or 2 is equal to x. That's called the symmetric property. Next, we have the transitive property. And the transitive property is something that you will definitely need to understand. So it says if A is equal to B and B is equal to C, then we have that A is equal to C. And that makes sense, Because we can say if 4 plus 3 is equal to 7 and 7 is equal to 9 minus 2, then we have that 4 plus 3 is equal to 9 minus 2. So we're just changing a little bit of the logic that's behind it. So we're saying if A is equal to B and B is equal to C, then A must also be equal to C. And if you need help like wrapping your head around that, please contact me and I can talk to you a little bit more about it. Finally, we're going to talk about one of the more confusing topics, and that's called the closure property. And basically, all it means to be closed under a certain operation, so we can be closed under addition, under division, under subtraction, under whatever operation. If the operation always produces an element, so a number that's in the same set, so we don't go to a different set, then we say that the set is closed. So for example, number 1, we have integers are closed under multiplication. So that's saying that if we multiply two integers together, we're always going to get an integer. And that makes sense because we only have the negative numbers, 0, and the positive numbers. So we can't really multiply two numbers and get a fraction with just integers. So we have that it's true. And make sure that you read directions here. It says answer true or false. If it's false, you're going to give a counterexample. So if it's false, what you're going to do is you're going to write why you think it's false. So give me the example that you thought of. So 2, the natural numbers, or remember the counting numbers, so 1, 2, 3, 4, and 5, and so on. The natural numbers are closed under subtraction. Is that true? Well, how about I give you a counterexample to show you that it's not. I know that we have two numbers. Let's say 5 and 9. And I know that 5 and 9 are both natural numbers. So if I subtract them, I should be able to get a natural number, or that's what we think. So what I'm going to do is I'm going to take 9 minus 5, and that gives us 4. So 4 is a natural number, so we're good there. But what if we switch the placements of 5 and 9? So instead, what if we have 5 minus 9? What does that give us? Well, negative 4. Is negative 4 a natural number? No, because we can't imagine negative 4 things. We don't know what that looks like. So this is an example of a counterexample. And that's what I want you to show me if something is false. So you have to give me an example that shows that it doesn't work. So number 2 would be false. Number 3, we have even numbers are closed under addition. So if you pick two random even numbers, let's say 2 and 6, if we add 2 and 6, what number do we get? 8. Is 8 even? Yes. So we can say that even numbers are closed under addition. So that's true. So another way to think about it is all the numbers are in a room, okay? And they can mingle with one another. They can shake hands, they can hug, they can do whatever they want. And as long as they don't go outside of that room, it's closed off. So we're going to call it a closed set. But if somebody, brings their friend over from a different class, then we no longer have that closed set. The door's open. So we're going to call it not closed. So number 4, we have irrational numbers are closed under division. Well, let's try the one irrational number that you should know right offhand, and it's pi. So what if we say pi divided by pi? What does that give us? Well, pi divided by pi is a fancy form of saying 1. And if we think about it, is 1 an irrational number? Does it have a never-ending decimal that never repeats? Well, no, it's 1. It just ends. So we can say that 1 is not an irrational number, and we've already provided a counterexample to show that this statement is false. And we're going to skip number 5, so we're just going to mark through it. So that's it for notes. You're going to have an assignment where you have to go through and either use the properties or identify what properties that the paper is using. In order to get credit for watching this video, I need you to take a picture of your completed notes and upload them to the folder that had this video. That way I can give you your points. That's all I have for you, and I hope that you have a wonderful Friday. Enjoy your weekend.